My name is Zhifeng Kong. I'm very happy to introduce our paper, Understanding Instance-Based Interpretability of Variational Auto-Encoders. This is a joint work with my PhD advisor, Professor Kamalika Chaudhuri. Modern deep neural networks can achieve very good performance on classification tasks. However, it is very hard to understand why these models make certain predictions. In the interpretability research, we aim to answer this question by generating interpretations that can be understood by humans. There are many works in this area. One class of works are called instance-based interpretability. We ask which training samples are most responsible for the prediction of a test sample. This question can be answered by influence functions. The influence function of a training sample xi over a test sample z is defined as the difference of the loss of the model trained without xi and the loss of the original model. If the difference is large, then xi is very important for z. So these methods are designed for classifiers or supervised learning. But what about unsupervised learning, where there are no labels? We formally frame the counterfactual question for instance-based interpretability in unsupervised learning. We ask which training samples are most responsible for increasing the likelihood of a test sample. It turns out that influence functions can readily answer this question with proper loss functions. What should influence functions tell us? What concepts are we interested in? We first define proponents and opponents to be the training samples that have very positive and negative influences over a test sample. So proponents increase the likelihood of test sample and opponents decrease it. Then we are interested in which training samples are strong proponents and opponents of test sample. We're also interested in another concept called self-influence, which is defined as the influence of a training sample over itself. In supervised learning, it closely connects to the memorization properties of training samples. So we are interested in which training samples have the highest and lowest self-influences, respectively. To get some intuitions about these two questions, we look at some classical unsupervised learning methods. Create a simple 2D data set and feed 3 different density estimators to this data set. We feed the k-nearest neighbor density estimator, the kernel density estimator. These two are non-parametric. We also have the Gaussian mixture model, which is parametric. We then look at influence functions in these 3 models. Self-influences. We plot all training data according to their self-influences. In k-nearest neighbor density estimator, high self-influence samples are from a cluster whose size is exactly k. In kernel density estimator, high self-influence samples are from a sparse region. And in Gaussian mixture models, high self-influence samples are more distributed. They are far away to each cluster center. We then use a test sample in the marked in the green cross symbol in the center of a cluster. We plot all training data according to the influences over this test sample. In all models, we find strong proponents are its nearby samples. However, it is very surprising and interesting to see that in Gaussian mixture models, strong opponents can also can also from the same class. So these are some intuitions in classical methods. We then or VAEs. These models are trained to maximize the evidence lower bound, the lower bound for log likelihood, which is also called the elbow. We also define influence functions via elbow. There are a few challenges. First, randomness. Elbow involves an expectation term, so the influence function cannot be exactly computed. To solve this problem, we look at the empirical average rather than the expectation, and establish a probabilistic bound on the difference of the empirical and the actual influence function. Another challenge is computation. The original influence function is very hard to compute, so we take advantage of a fast first-order approximation called trace-in supervised learning, and introduce VAE trace-in based on this algorithm. It is much more computationally efficient. We then evaluate VAE tracing on MNIST and Cipher-10 datasets. Self-influences. We plot high and low self-influence samples in the following figures. These are high self-influence samples. We find they are very hard to recognize, they're visually high contrast, they're complicated and difficult. And these are similar to supervised learning as well. As for low self-influence samples, they have similar simple shapes and share similar backgrounds. Test samples, the strongest proponents and opponents in the following figure. In MNIST, we find the strong proponents and opponents are similar samples in the same class. Quantitatively, roughly 80% of the strongest proponents and 40% of the strongest opponents have the same label as the test samples, and both proponents and opponents are close to test samples in the latent space. And this is very similar to Gaussian mixture models we talked about before. In Cipher-10, things are a little different. Strong proponents tend to match the color of the images, and they tend to have very large norms, indicating they are high contrast or very bright. This has also been observed in supervised learning. As for strong opponents, they tend to have very different colors. In conclusion, in this work, we investigate instance-based interpretability for unsupervised learning. We frame the counterfactual question and use influence function to answer this question. We then look at influence functions in classical unsupervised learning methods to get some intuitions about it. We look at VAE and present VAE trace-in algorithm for it. It is both computationally efficient and theoretically sound. We extensively evaluate VAE tracing algorithm on several real-world datasets. An important future direction is to investigate instance-based interpretability methods for larger models trained on larger datasets.